The autumn of 1943 found Britain's aircraft designers in a desperate race against time and physics alike. At Supermarine Aviation Works in Southampton, mechanics laboured beneath industrial lights while rain hammered relentlessly against the hangar roof. The Spitfire Mark 21 sat before them like a puzzle that refused to solve itself, sleek and promising on the surface, yet fundamentally broken in ways that no conventional thinking could fix. The aircraft represented everything the Royal Air Force needed during this critical phase of the war: speed, firepower, the legendary agility that had kept Hitler's bombers at bay during Britain's darkest hours. But the Rolls-Royce Griffin engine, which should have been the answer to every pilot's prayers, had instead become a nightmare. Nearly 2,000 horsepower of raw, uncontrolled fury that twisted the fuselage like a piece of cork caught in a whirlpool. Squadron leader James McKinnon climbed down from the cockpit, his flight suit soaked through with perspiration despite the October chill that bit through the hangar doors. His hands still trembled slightly as he peeled off his leather gloves, not from fear, but from the sheer physical battle of forcing 2,000 horses through the Hampshire sky without being torn apart by the machine itself. Every muscle in his shoulders ached. Every nerve felt raw. Chief Engineer Malcolm Whitfield was waiting, reading the answer in McKinnon's face before the pilot even spoke. Whitfield had learned to interpret the subtle language of exhaustion and frustration that every test pilot brought back with them. At 350 miles per hour, "She wants to roll left so hard I nearly put her into a spin," McKinnon said, his Scottish accent thick with the weight of frustration. "The torque from that engine, it's like the propellers are trying to tear the nose clean off the airframe. Above 400 miles per hour. Forget about it. No pilot on Earth could hold her straight in combat." The problem came down to physics, though that hardly made it easier to solve. The Griffin 65 engine generated 1,080 horsepower at sea level, nearly double what the earlier Merlin engines had produced. That should have meant 470 miles per hour and superiority over every German fighter in the sky. Instead, it meant something far more sinister. Every revolution of those massive four-bladed propellers generated a rotational force that fought against the aircraft itself, trying to twist the entire frame in the opposite direction. Whitfield ran his hand along the propeller hub, feeling the subtle vibration that never quite stopped, even when the engine sat silent and cold. At low speeds, a skilled pilot could compensate. Rudder input, muscle memory, raw determination. But as airspeed climbed, the aerodynamic forces amplified the problem until it became exponential, the aircraft that grew more dangerous with every mile-per-hour increase, when what the war demanded was the exact opposite. "We can't simply work around physics, Malcolm," McKinnon said, shaking his head sharply. "This isn't something pilot training can fix. At the speeds we need for air superiority over Western Europe, this machine is becoming unflyable, full stop." Everyone understood what he wasn't saying. If they couldn't solve this, the entire program would collapse. The Ministry of Aircraft Production had already poured millions into development. Production schedules called for hundreds of these aircraft rolling off assembly lines within months. The Royal Navy needed the naval variant for the Pacific Theater, where American carrier fighters had already proven their worth in battle. Failure would mean far more than a simple setback. It would represent a catastrophic gap in Allied air power at the war's most critical moment. 15 miles away, in a cluttered office surrounded by scattered technical drawings and empty teacups, Joseph Smith was wrestling with the problem from a completely different angle. At 42, Smith possessed something that bordered on genius where aerodynamics were concerned, though his solutions often struck his more conservative colleagues as unnecessarily complicated or impractical. He had spent the past week analyzing every scrap of flight data, searching for something that others increasingly believed simply didn't exist. The conventional answers had all failed. Enlarging the rudder added weight and drag without addressing the fundamental problem. Adjusting the engine mount reduced torque transmission but weakened the airframe. Modifying propeller blade angles helped marginally while creating new headaches with vibration and efficiency. Then, on a grey October afternoon, Smith set down his calculations and looked at the problem differently. Instead of fighting the Griffin's rotational energy, what if the answer was to harness it? The concept was elegant in its simplicity, yet staggering in its complexity. Two propellers mounted on the same shaft, spinning in opposite directions, would cancel each other's torque reaction while delivering unprecedented thrust efficiency. One propeller would spin clockwise while the other turned counterclockwise, their rotational forces neutralizing each other like dancers moving in perfect synchronization. But the engineering challenges were monumental. The system would require a complex gearbox to drive both propellers from a single engine output, adding weight to an aircraft already pushing structural limits. The contra-rotating propellers would need precision balancing to prevent catastrophic vibrations that could shake the machine apart mid-flight. The entire assembly would have to endure the violent stresses of combat maneuvering. Most critically, everything would have to work reliably enough for wartime mass production and maintenance under field conditions that were far from ideal. When Smith presented his drawings to the Royal Air Screws engineering team, the reaction was swift and overwhelmingly negative. Senior engineer Robert Morrison called it a Rube Goldberg contraption that no factory could manufacture in quantity. Production manager Charles Henley worried about weight penalties and maintenance nightmares. Test engineer David Clark questioned whether the system could survive carrier operations aboard naval vessels. "It's too complex by half," Morrison argued, his voice rising during a heated conference in Smith's office. "We're talking about building two complete propeller systems and making them work perfectly together. The gear ratios alone require precision manufacturing that we can barely manage in peacetime. In wartime, it's simply impossible." Yet Smith had done his calculations with meticulous care. Yes, the contra-rotating system would weigh roughly 200 pounds more than conventional single propellers. But by eliminating torque reaction entirely, the aircraft could finally achieve its full potential speed. More importantly, the improved propeller efficiency would increase thrust by nearly 15%, more than compensating for any weight penalty. The Spitfire Mark 21 could become the interceptor that Britain desperately needed. As winter approached, Smith's proposal would determine far more than just the fate of one aircraft. It would shape the balance of air power over the battlefields of Europe and the Pacific. The Ministry of Aircraft Production's boardroom in London felt less like a place for engineering discussion and more like a tribunal when Joseph Smith arrived on the morning of November 15, 1943. Mahogany tables gleamed beneath the weight of decisions already made and yet to come. Around them sat some of Britain's most senior aviation officials, their faces bearing the accumulated exhaustion of a war that had already consumed 4 years with no end in sight. Air Marshal Sir Wilfrid Freeman presided with the grim efficiency of a man who had watched too many promising designs fail precisely when the nation needed them most. "Mr. Smith," Freeman began, his voice carrying the clipped authorities of someone accustomed to being obeyed, "we have reviewed your proposal for the contra-rotating propeller system. I must tell you that our technical staff remains deeply skeptical." Freeman gestured toward an intimidating stack of reports and memoranda. "The general consensus is that your design introduces unnecessary complexity at a moment when we require proven and reliable solutions." Smith had anticipated resistance, but the formal setting still made his throat tighten. These men controlled British aviation's destiny. Their decision would determine whether his calculations and sleepless nights meant anything beyond academic exercise. "With respect, sir, the complexity is precisely what makes the system effective," Smith replied carefully. "We are not simply adding components. We are fundamentally solving the torque problem that has rendered the Griffin engine unusable at combat speeds." Sir Roy Fedon, Director of Technical Development and one of Britain's most accomplished engine designers, leaned forward with visible skepticism. "Your proposal calls for a gearbox system that would make this propeller assembly the most complex ever fitted to a fighter aircraft, Mr. Smith. We are discussing contra-rotating shafts, planetary gear reduction, and precision timing that must remain perfect under combat conditions. The maintenance requirements alone could ground entire squadrons." Smith had prepared for this objection. "The gearbox complexity is manageable with proper manufacturing tolerances. Rolls-Royce has already demonstrated that complex propeller systems can be mass-produced through their variable pitch mechanisms. Our system would use a 2-stage planetary gear train with a reduction ratio of 0.771 for the forward propeller and 0.62 to 1 for the rear. The differential rotation speeds would be precisely calculated to cancel torque while maximizing thrust efficiency. Group Captain Peter Thornton, representing operational requirements, consulted his folder of combat reports from Mediterranean and Pacific theaters. Even if your system functions mechanically, Mr. Smith, we are concerned about weight and balance. The Mark 21 is already heavier than earlier Spitfire variants. Adding 200 pounds of additional propeller machinery introduces variables we do not fully understand. Smith pulled out his most carefully prepared calculations. The weight penalty exists, but the performance gains more than compensate. Our estimates demonstrate a 15% thrust increase combined with complete elimination of torque reaction. The aircraft would not only achieve its design speed of 470 miles per hour, but maintain controllable flight characteristics throughout the entire speed envelope. Current test flights show the Mark 21 becoming increasingly dangerous above 350 miles per hour. Our system would extend safe operation well beyond 400. Intelligence reports had just confirmed what the Allies suspected. The Germans were pushing ahead with dangerous innovations. Messerschmitt's engineers were working on souped-up versions of their Me-262 jet fighter, while Focke-Wulf kept perfecting their high-altitude TA-152. The competition for air superiority was intensifying fast, and with the invasion coming, the Allies needed every edge they could grab in speed and handling to keep command of the skies above Western Europe. Freeman looked over his notes carefully, weighing the promise of this new approach against the real engineering risks sitting right in front of him. Your idea would mean reworking production lines pretty substantially, Freeman said. How much time are we really talking about if we give this the green light? Smith didn't hesitate. 6 weeks to get the first gearbox designed and built in the shop. Then another 4 weeks for the propellers themselves. They'd need careful fabrication and balancing. If everything went according to plan, he said, they could have something ready for flight tests by early February. What Smith was proposing seemed simple enough on paper, but the reality was intimidating. The contra-rotating system demanded precision work that would strain Britain's best manufacturing. Each propeller would have to be perfectly balanced. We're talking tolerances measured in ounces, while the gearbox needed gear-cutting accuracy normally reserved for fine chronometers. These weren't ordinary tolerances. They were asking for absolute perfection. The room went quiet as the officials took it all in. Half a year had already passed since that first problematic test flight of the Griffin-powered Mark 21, and pilots in operational squadrons were getting impatient. They wanted aircraft that could match what the Germans were flying, especially at altitude where the Griffin's power should have given them a real advantage. Air Commodore Ralph Sorge, the senior figure who'd guided fighter development through the Battle of Britain, finally spoke up. He fixed his eyes on Smith. Your reputation speaks for itself. When someone of your standing proposes something this bold, people pay attention, but I need you to answer me straight. Can you guarantee this will actually work? We can't take another failed modification program. Smith met his gaze without wavering. Sir, I'm putting my career on the line. The physics check out, the engineering is within our reach, and the performance boost is exactly what the Royal Air Force needs right now. He paused, letting the words carry weight. The Spitfire Mark 21 with contra-rotating propellers will be faster and more nimble than anything the Germans have in the sky. It was a bold claim, hanging there in the room like a dare. Freeman caught the eyes of his colleagues across the table. They all recognized the same thing. Smith wasn't just spouting confidence. This was someone who actually knew his field. The man had engineered propeller systems for Britain's greatest aircraft. His history showed that when others hit dead ends with standard solutions, Smith found ways through. Freeman made his decision. Very well, we'll authorize a limited program. 1 prototype installation, full flight trials, complete evaluation. But listen carefully, Mr. Smith. If this fails, or if it pushes back Mark 21 production even by a month, the damage goes way beyond your career. Smith gathered his papers as the meeting wrapped up, feeling the weight of what he'd just committed to settle over him like concrete. The coming months would show whether his idea would transform fighter aviation into something revolutionary, or become another lesson in how unchecked ambition could derail engineering logic. Everything hinged now on gears and shafts and propellers spinning in ways that broke every rule of conventional aircraft design. The war wouldn't pause while they chased perfection. But sometimes radical thinking was exactly what turned the impossible into weapons that actually changed battles. February 23, 1944, brought grey, bitter weather to the experimental airfield at Boscombe Down. Wind gusted hard across the runway, 25 knots cutting across everything. Inside Hangar 7, the modified Spitfire Mark 21 looked almost alien, sitting among the rows of standard fighters. The massive contra-rotating propeller assembly dominated the nose like something predatory. The twin propellers, each stretching 11 feet across, created an optical effect that seemed to violate every law of aviation. Squadron leader Geoffrey Wellham walked toward the aircraft with the focused attention of a man about to stake his life on an unproven idea. At 24, he'd already logged 3 years in combat, over Britain, France, and Malta. Nearly 800 hours behind the stick in different Spitfire models. His reputation for detailed aircraft evaluation had gotten him assigned to the most experimental programs. But nothing had quite prepared him for the mechanical complexity bolted onto the nose of Spitfire RK958. 6 months of intensive work by Smith's team at Rotol had gone into this propeller system. The forward propeller turned clockwise at 1,125 revolutions per minute. The rear spun the opposite direction at 1,175. Between them sat a gearbox weighing 193 pounds, machined to the precision normally demanded by watch manufacturers. Every part had been balanced within half an ounce. Yet the whole thing still vibrated with a pulse that seemed to move through the airframe like a second heartbeat. Chief Test Engineer Michael Lithgow checked everything before flight, moving through the inspections with barely concealed tension that spread through the hangar. The gearbox temperatures were holding normal during engine running. He gave Wellham the update while glancing down at his clipboard full of measurements. Oil pressure sitting at 60 pounds per square inch across the power range. But Geoffrey, those harmonic vibrations at 1,800 engine RPM, we still can't explain them fully. Wellham ran his hand across the propeller hub. Compared to a normal single propeller, this looked impossibly elaborate. What's the test plan? Conservative, Lithgow said. Climb to 8,000 feet, level flight at different power settings, then gradually push the speed up toward 400 miles per hour. If the aircraft stays controllable, we want to watch the torque reaction behavior and see if anything unusual comes up with the handling. Smith stood quietly off to the side near the aircraft's wing, his face giving nothing away about the sleepless nights he'd just endured. This morning meant everything. The peak of his career, but it also carried the possibility of disaster that wouldn't just wreck his reputation, but could kill Wellham. Every calculation had been verified repeatedly, every component tested beyond failure points, yet aircraft design remained partly mystery, partly craft. At 9:15, Wellham lowered himself into the familiar Spitfire cockpit, except nothing felt entirely familiar anymore. The instrument panel now bristled with extra gauges, engine oil temperature, gearbox oil pressure, forward propeller pitch, rear propeller pitch. Every parameter demanded attention on what should have been routine operations. The Griffin engine fired with its deep, characteristic rumble, but the sound transformed immediately through the contra-rotating propellers into something altogether different. Where a single propeller would create that familiar rhythmic pulse, these twin assemblies generated a complicated harmonic that seemed to vibrate right through the pilot's skeleton. Ground control cleared him for takeoff at 9:32. Wellham eased the throttle forward with careful precision. The Spitfire rolled down the runway with unexpected smoothness. The contra-rotating propellers were doing what they were designed to do, eliminating the leftward turning force that every Spitfire pilot normally had to fight with right rudder. For the first time in months of testing, the Mark 21 stayed centered on the runway without constant pilot corrections. Rotation happened right at 85 miles per hour, exactly predicted. But Wellham immediately sensed trouble. The climb felt weak. It wanted more power than expected to hold a decent rate of ascent. The extra weight of the propeller system was hammering performance worse than Smith's math had indicated. By 5,000 feet, Wellham was nearly at full throttle just to maintain 2,000 feet per minute climb rate, numbers that should have come easily at just 75% power. He reached for the radio. "Boscombe, this is Test 27. Power requirements are running higher than expected on climb. Requesting permission to level off at 6,000 feet for handling checks. Test 27, you're cleared to level flight." "How's she handling?" came the response. Wellham pulled the power back to cruise settings. What he found surprised him. Despite the climb struggles, the Spitfire felt remarkably steady and responsive in level flight. Eliminating that torque reaction had changed how the aircraft behaved in ways that went beyond just directional control. The whole airframe seemed more stable, more predictable, as if the contra-rotating propellers had somehow brought the Griffin's wild energy under control. At 300 miles per hour, an aircraft that had previously tried to roll unpredictably now flew with steady, crisp precision. Wellham tested gentle turns, steep banks, quick direction reversals. The Mark 21 responded with agility that seemed impossible for something this large and heavy. The torque elimination had restored the legendary Spitfire handling that made the type legendary during the Battle of Britain. Then Wellham pushed the throttle toward maximum power, and everything changed. Instead of smooth acceleration toward top speed, the Spitfire began shaking with increasing violence. At 370 miles per hour, the whole frame vibrated so intensely that reading instruments became nearly impossible. The contra-rotating propellers, supposedly working in perfect harmony, were creating destructive waves through the airframe that threatened to tear it apart. Boscombe, Test 27, experiencing severe vibration above 370 miles per hour. Wellham's voice stayed tight as he backed off the power to stop the shaking. "I'm coming back in for emergency landing." The approach itself revealed another unexpected problem. With power cut to idle, the Spitfire descended faster than normal, needing constant power adjustments to maintain proper descent angle. The extra weight and changed aerodynamics of the contra-rotating system had shifted the aircraft's flight envelope in ways Smith's team hadn't fully worked through. Wellham touched down at Boscombe Down after 43 minutes in the air. His expression showed the grim awareness that Smith's revolutionary design had stumbled on its crucial first test. The contra-rotating propellers did exactly what they were supposed to do, solved the torque reaction problem. But they'd created new problems that might turn out to be even worse than the original Griffin troubles. As ground crews examined the aircraft for damage from those violent vibrations, Smith walked over to Wellham, knowing he was watching his life's work potentially fall apart. The test pilot's report would decide whether the project moved forward or joined the graveyard of brilliant ideas that couldn't survive reality. 2 hours after landing, the emergency meeting packed Hangar 7. Smith found himself facing engineers, test pilots, and ministry officials whose looks ranged from disappointed to openly furious. The modified Spitfire sat silently behind them, those contra-rotating propellers now motionless but still seeming to radiate mechanical threat. Air Commodore Sorge had driven down from London immediately after hearing Lithgow's initial report. His presence turned what should have been a technical discussion into something more like a trial. Squadron Leader Wellham, Sorge's voice carried institutional weight. "Give us everything about how the aircraft performed today." Wellham stood at attention despite the sweat stains from battling an aircraft that had nearly shaken itself to pieces. "Sir, the contra-rotating propellers completely eliminated torque reaction during takeoff and low-speed flight. The aircraft tracked perfectly down the runway without any rudder work. Handling below 300 miles per hour felt exceptional, possibly the best I've experienced in any Spitfire variant." A ripple of surprise moved through the gathered engineers. Despite how the flight ended, Wellham's early assessment showed Smith's basic concept had actually worked, had actually solved the Griffin engine's main problem. But his tone grew more serious. Above 370 miles per hour, severe vibrations made further acceleration impossible. "The frame shook so hard, I genuinely feared structural failure. Plus, climb performance was significantly down. We needed nearly full power for climb rates that should have taken just 75% throttle." Smith carried the weight of disappointment on his shoulders like a heavy stone. Half a year of meticulous calculations, manufacturing excellence, and his entire professional standing had resulted in an aircraft that performed beautifully at slower speeds, yet turned dangerously unpredictable precisely when peak performance mattered most. The bitterness of the contradiction cut deep. He had resolved the torque issue only to introduce vibration problems that seemed even more treacherous than what they'd replaced. Chief Engineer Lithgow studied the technical data spread across his clipboard, searching for any possibility of salvaging something from the day's devastating failure. The ground tests had revealed harmonic vibrations tied to specific engine speeds, but nothing approaching the intensity that Squadron Leader Wellham had encountered during flight. The aerodynamic forces at high speed were apparently triggering resonances within the propeller system that nobody had foreseen. Director Fedine shifted forward. His reputation for technical rigor made his inquiry particularly demanding. Mr. Smith, your original calculations surely took into account the aerodynamic forces acting on the propeller assemblies. How do you account for this gap between what you predicted and what actually happened? Smith had spent the previous 2 hours grappling with that identical question, and his response captured the fundamental challenge facing aviation engineers during wartime. Sir, our calculations drew from static ground testing and wind tunnel investigations. The way two counter-rotating propellers behave in genuine flight conditions, especially at high velocities, creates aerodynamic effects that are extraordinarily difficult to forecast without genuine flight evaluation. The vortices generated at the propeller tips seem to be producing destructive interference patterns we hadn't detected in our laboratory investigations. The answer was technically valid, but it brought little reassurance to administrators who had invested substantial time and resources backing Smith's experimental design. Air Commodore Sowerley's face suggested he was already measuring the political fallout from another unsuccessful aircraft program. The critical question, Sowerley stated, his tone sharp, is whether these difficulties can be fixed in a practical time frame, or whether we should abandon this direction and pursue conventional solutions to addressing the Griffin's torque trouble. Smith sensed his future hanging precariously, yet his engineering instincts pushed him to refuse giving up without investigating every conceivable avenue. Sir, I'm convinced the vibration difficulties can be resolved through adjustments to the propeller blade design and gearbox synchronization. The core principle is fundamentally sound. We simply must eliminate the aerodynamic interference generating the destructive resonance. Test pilot Wellham, having personally risked serious injury in the morning's flight, surprisingly found himself aligned with Smith's assessment. If I may say so, sir, the aircraft's behavior below 370 miles per hour was extraordinary. If Mr. Smith can resolve the high-speed vibration challenge, we'd have something with the Griffin's raw power combined with control characteristics surpassing any current fighter. The room became still as officials weighed technical excellence against the pressure for quick results. Intelligence from Allied sources suggested German aircraft developers were creating advanced new fighters, while preparations for the European campaign, though still weeks away, were consuming tremendous resources and demanding absolute command of the air above any landing zones. Smith seized the opening to present his answer. The vibration analysis indicates the issue stems from how propeller blade angles connect with rotational speeds. By adjusting the gear ratios to modify the rotational speed difference between forward and rear propellers, we can move the harmonic frequencies away from the critical resonance areas. Additionally, redesigning the blade twist shape should decrease vortex formation at the tips. Lithgow glanced up from his calculations with measured hopefulness. The modifications Mr. Smith proposes would need approximately 3 weeks of machine shop fabrication and another week for rebalancing the complete assembly. We could have the aircraft prepared for the next round of testing by mid-March. Air Commodore Sowerley checked his pocket watch, plainly weighing time demands against other pressing requirements. The Aircraft Production Ministry faced intense pressure to produce aircraft ready for combat, and every day devoted to experimental work meant fewer operational squadrons available for potential deployment in Europe. Mr. Smith, Sowerley said after deliberation, you receive one final opportunity to validate your system, but comprehend that this represents the maximum tolerance we can allow for experimental efforts. Should this second test flight fail to demonstrate meaningful improvements, we will suspend the counter-rotating propeller program entirely and commit our focus to traditional torque reduction approaches. Once the meeting concluded, Smith lingered alone in the hangar, gazing at the stationary Spitfire embodying both his most accomplished technical accomplishment and his most painful professional setback. The aircraft seemed unremarkable now, standing silent and still. Its sophisticated propeller arrangement was simply machinery awaiting adjustment. Yet Smith's engineering mind already perceived the modifications necessary to reshape his partially realized experiment into the transformative weapon he had envisioned. The subsequent 3 weeks would establish whether Joseph Smith's unconventional thinking would reshape fighter aircraft advancement or become a warning about overconfidence in radical methods during global conflict. The destiny of Britain's most recognized fighter aircraft now rested on gear configurations, blade angles, and propeller physics that most aviators never examined closely. As February darkness deepened around the airfield, Smith began sketching the modifications that would vindicate his creative approach or permanently damage his aviation career. The dawn of March 18, 1944, delivered clear skies and gentle winds to Boscombe Down, conditions appearing almost ideal for what everyone recognized as the decisive evaluation of Smith's contentious propeller configuration. 3 weeks of concentrated work had restructured the counter-rotating system into a version that appeared subtly altered from the original, though these improvements remained invisible to anyone lacking detailed familiarity with propeller blade geometry and gear specifications. Smith had endured sleepless nights rechecking each component of the system, particularly concentrating on harmonic frequencies that had nearly wrecked the aircraft during its initial flight trial. The answer involved changing the rotational velocity connection between the two propellers from the initial configuration of 1825 and 1475 revolutions per minute to a revised setting of 1750 and 1500 revolutions per minute respectively. The smaller speed gap would shift the critical resonance frequencies beyond the aircraft's normal operating range, while maintaining the torque reduction capability, making the arrangement important. Beyond this, Smith's team had revised the blade twist configuration on each propeller, minimizing the severe angle transitions close to the tips that promoted vortex generation. Every blade now incorporated a more uniform progression from base to extremity, meant to suppress the aerodynamic interaction, producing vibration at elevated speeds. The modifications required finishing each blade individually to tolerances approaching fractions of an inch, labor demanding approximately 2 weeks of precise work. Squadron leader Wellham examined the revised Spitfire with qualified hope, yet memory of his previous flight's terrifying conclusion kept enthusiasm measured. From distance, the aircraft appeared unchanged, but careful observation revealed the refinements that might convert it from risky experiment to actual breakthrough. The propeller blades captured morning illumination in modified ways, their updated geometry producing shadow formations that conveyed greater intentionality than the earlier design. The gearbox modifications demonstrated flawless function through ground operations, Chief Engineer Lisco indicated, though his tone reflected the apprehension of someone recognizing that ground conditions predicted nothing regarding actual flight performance. We attained consistent operation across the entire power spectrum without the harmonic vibrations damaging the first version. Engine temperatures stayed regular, and the revised gear settings eliminated the resonance frequencies we identified through analysis of the earlier failure. Air Commodore Sowerley had journeyed from London explicitly to observe this evaluation, conveying an institutional sense of finality affecting everyone gathered. The Aircraft Production Ministry lacked capacity for endless experimental endeavors, particularly when standard aircraft faced urgent operational demands for the coming European invasion. This test would establish not merely Smith's systems prospects, but the entire orientation of upcoming British fighter advancement. Precisely at 10:15, Wellham activated the Rolls-Royce Griffin power plant and instantly registered differences from the prior attempt. The acoustic signature was distinctly changed, retaining the intricate tones created by opposing propellers, yet displaying more regulation, diminished mechanical intensity. Engine instruments revealed expected parameters as he increased throttle for runway movement, and directional control remained constant without the tremor characterizing the previous system's ground operation. The departure at 10:28 demonstrated the most striking enhancement. Whereas the initial flight demanded substantial throttle to accomplish adequate climbing ability, the adjusted aircraft climbed at 2,000 feet each minute, utilizing merely 80% capability. The redesigned propeller shape had seemingly removed considerable aerodynamic drag, limiting the original configuration, permitting the Griffin's complete output to convert into genuine performance. Boscombe Control, Test 27 ascending through 8,000 feet, Wellham transmitted, excitement discernible within his voice. Climb performance shows substantial improvement versus the preceding test. Handling continues excellent. Requesting clearance to evaluate speed performance. The authorization arrived immediately. Test 27. You're authorized for speed evaluation. Use extreme care approaching previously problematic altitudes. Wellham leveled the Spitfire at 10,000 feet and initiated deliberate investigation of the velocity range that had nearly destroyed him weeks prior. Traveling 300 miles per hour, the aircraft demonstrated the smooth precision recalled from quality traditional Spitfires. At 350 miles per hour, still absent concerning vibrations or behavior issues. When the speed gauge approached 370 miles per hour, the velocity triggering the initial system's destructive reaction, Wellham braced himself against the violent trembling that had compelled his emergency landing. Rather than this anticipated trauma, the Spitfire persisted accelerating without interruption. At 400 miles per hour, the aircraft registered more composed than most contemporary fighters at comparable speeds. The suppression of torque forces paired with vanquished vibration complications had generated something unprecedented in contemporary aviation. A powerful fighter growing progressively more responsive as it approached its performance boundaries. Boscombe Control Test 27 has reached 410 miles per hour, displaying no adverse handling. Wellham broadcast, his voice now transmitting authentic enthusiasm rather than constraint. The aircraft operates with complete stability and responsiveness. This demonstrates exceptional capability. From the control tower, Smith observed through optical magnification his modified Spitfire executing crisp maneuvers against the azure Hampshire horizons. The counter-rotating propellers converting the tremendous Griffin output into velocity and maneuverability, apparently contradicting fundamental aeronautical principles. The accomplishment vindicated not simply months of engineering endeavor, but his fundamental conviction that established methodologies were inadequate for contemporary warfare challenges. Wellham extended his evaluation across another 25 minutes, investigating each component of the aircraft's performance spectrum. Elevated velocity plunges demonstrated the Spitfire could surpass 450 miles per hour in controlled descent without manifesting the compressibility complications hampering numerous high-capability fighters. Sustained maximum power turning exhibited command merging prior Spitfire nimbleness with Griffin-powered performance. Landing near 11:32, Wellham proceeded to the maintenance facility, displaying the demeanor of someone who had experienced something authentically transformative. Upon shutting down the power plant and descending from the pilot position, his opening expression to engineers and officials carried the substance of years invested in operational aviation. "Gentlemen," Wellham declared, extracting his protective headgear and regarding Smith intently, "what you have constructed transcends a mere improved Spitfire. This represents the most exceptional fighter aircraft I have commanded through the atmosphere. The amalgamation of velocity, handling sophistication, and reaction surpasses all existing operational equipment anywhere." Air Commodore Sowerly moved toward Smith, his countenance transformed from questioning skepticism to obvious regard. The productive evaluation had established the credibility not simply of the technical methodology, but the strategic judgment to investigate unorthodox answers to apparently insurmountable challenges. "Mr. Smith," Sowerly stated with formality, "congratulations appear justified. Your counter-rotating propeller arrangement has exceeded even our most ambitious performance expectations. The subsequent inquiry concerns manufacturing implementation speed for operational deployment." As the gathering of engineers and officials assembled beside the restored Spitfire, Smith encountered the fulfillment of confirmation, yet recognized the substantial obstacles ahead. Confirming the system's viability represented merely the commencement. Converting experimental accomplishment into real combat effectiveness demanded manufacturing accuracy, aviator instruction, and organizational management requiring resources testing Britain's industrial capabilities thoroughly. Nevertheless, in this immediate time frame, positioned beside the machine transforming his revolutionary concept into tangible accomplishment, Smith permitted himself envisioning counter-rotating Spitfires achieving supremacy across European skies. Their remarkable performance and exceptional handling potentially furnishing the competitive advantage that could change the war's trajectory itself.